Welcome, everyone. My name is Victor, and today I'm going to talk to you about a couple of experiments that we made at PagerDuty, in particular of how we built our SRE agents. I want you to feel like you with us on a journey of making decisions and the trade-offs. And essentially, this talk is about how we decided to go into multi-agents and the decisions we took along the way. Let's get started. So this talk is essentially, we're going to try to answer three questions about why would we even want to do many agents, like why one is not enough. And if you want to do many agents, what does it really look like? And how complex is it really? Do you just add more agents and it just works, or, right? So let's start with why. Not so long ago at PagerDuty, this is how our agent used to look like, very simplified. We had a single agent that could talk to engineer. It has some checkpoint. And our SRE agent in particular, over the time, as we started, it was very good at solving the incidents and triaging them and figuring out the run book, narrowing down the possible root cause candidates and things like that. But as we went into more complex incidents with more possible problems that caused the breakage, we figured out that systematically our agents started to not be very accurate at solving very complicated incidents. And according to the research we also did, this was not only us who felt that. So if you're building an agent yourself, you probably might feel similar problems that you probably cannot fix if you just tweak the prompt. One of them is what is called context rot. So you might have noticed if you speak to an agent and over time, if your conversation is getting too long, the initial content of the conversation gets forgotten by the agent because it wastes less in its attention span. So it rots the context. And especially is the case if you ask the agent to do something very complicated for a very long period of time. The next thing we figured is instruction overload, which is essentially if you have an agent, you wanted to do more things over time, you add new features, and adding new features not necessarily makes it better at the feature that you used to do. For the feature that it used to do well, over time as we added new things, it started to do the things that used to do well, less well, because essentially it has to do many things now, so it's not as good at doing them. And all of this is sequential. So you have only one agent, so it can only do one thing at a time. And if you have a complicated thing to do, it has to do like iteratively one after the other. And finally, you don't have interactivity. You dispatch the agent to solve a problem for you, but you cannot intervene. If the agent is going the wrong direction, you cannot course correct it. If the agent has some new finding, it doesn't update you, so you have to wait. And all of these problems are solvable, but they're not solvable by tweaking your agent itself. The solution to it, it's quite mature in the industry right now, is to add more agents. But what is really adding more agents, right? There are many ways of doing that. One of the common patterns of adding more agents is the orchestrator and sub-agents pattern, where you have basically a parent agent who decides what needs to be done, and it spawns as many agents as it needs to do the things. So to address the problems that we just mentioned in the why, the first couple of things that we might probably understand from having many agents is same as with humans, right? If you have tasks that you can parallelize, then it will be done faster because you have two agents or three instead of one. You also have better accuracy because one agent doesn't have to focus on everything at once. It just focuses on its own task, and the other also focuses on its own task. So the context doesn't get rotted like before. And finally, if you play your cards, you can get also interactivity, which is what we wanted in our SRE agent. We want the SRE agent to be able to do things, solve the incidents for us, but solving the incident is a long task. It's not something you do in a minute or two. Sometimes it lasts tens of minutes, 20, because incidents are complex and the systems are difficult. So you want interactivity. You want the agent to update you as you go. And you want the opposite. You want to tell the agent, hey, I know something else, so maybe you should take this into account rather than wait until the end and then start it again. So we got our list of things that we want now. We want things fast, accurate, and interactive. But things are not just you don't just get them, right? You need to find a way how you're going to run the agents when you have many of them, when you have a system of the agents. And there's a couple of ways to do them. So this is what we're going to talk now. So the first, the most naive approach is a sequential. In this approach, you have one agent that waits for the next one, then for the next one. So in this diagram, you can see you will spend 10 minutes. You might be thinking, why would I even want that if I have one agent that can also do sequential stuff? But actually, you already get better accuracy. So this is probably the thing you might want to do first, because if you do it, you already get better accuracy, and it's also least difficult to do. As we went deeper into our experiments, the next thing that naturally you might want to do with your agents is to make them do things in parallel. You have 3 of them. Why not start them at the same time? You get faster responses. At our experiment, we actually tried to do it with laser doesn't go there. If you at PagerDuty, we tried with LangChain deep agents, specifically sub-agents feature. At the time, there was no async agent, so this one was the one we went with. It worked for parallel, but it still doesn't give you interactivity. Why? Because it keeps working in a synchronous manner. You dispatch your main agent, and the main agent dispatches sub-agents in parallel, and you get a synchronous execution, you get the response back, but you have to block your main agent until all of this happens. So the natural next step that you might want to do is to achieve the true interactivity, which is what we're going to focus in on the next slides. But just to get your understanding, it's better than true parallel in the sense that the main agent just dispatches sub-agents as background agents, and it's free to do other things. So it's not blocked. So it can update the user about, hey, one sub-agent resolved, this is the findings, and also it can receive the input from the user and inject new facts about the investigation. And based on those facts, it might even spawn another agent to continue the investigation, to fact check if what user says is correct. So now we know what we want. We want true interactivity. We want background agents that will run independently without blocking the main one. So how did we do that? And there are many ways to do that, but at our experiments, what we did was this approach. So you might feel like if you're building multi-agents, you do it similar or might do it different. These were the experiments that we made. And at the time, we thought it was the best thing. So we learned from the previous experiment that we couldn't use LangChain sub-agents feature because it doesn't give us the asynchronous background agents. So we went a level deeper, and at PagerDuty, we use LangGraph. So our natural reflex was to use LangGraph for that. And the way we do it, you have the main agent, which essentially decides, okay, I need to create more sub-agents to do tasks, and it will interrupt. So in LangGraph, there is a feature that is called interrupt and resume. And if you are familiar with the framework, the way you would use that is if you want a human in the loop. For example, an agent is doing something that requires privileged execution, it will interrupt, it will ask human approves, resume. We use the same, except instead of human, we have sub-agents. Sub-agents do things, then they will say, okay, I finished, now we can resume. So the natural question from this approach to begin is, okay, you spawn the agents, but how do you get response back? Because we gave away the feature of synchronous request response that gives us responses out of the box. The agents now run asynchronously. This is not an unknown thing to do in distributed systems. After all, sub-agents are just programs. Now you can do it in Kafka, like with the topics, but we didn't want to overcomplicate our experiment. So we went with a simpler solution, or at the time we thought it was simple, and more on that later. So we went with webhooks, where essentially when main agent interrupts, it will spawn the sub-agents. It will tell them, this is the webhook you should answer to once you finish. And this is the way the main agent will receive the response back. Now, this is how far the experiment went in the start. And if you've been in backend development for some time, you might spot a race condition. Imagine 2 sub-agents finished at the same time. Main agent can process only one message at a time. It's only one. so the message will be lost. This is solvable with a queue, so we added a queue. Now instead of waiting for the webhook, the agents just know they have to write to the queue. It can be a mailbox in memory or Redis queue or what you choose. And as the queue gets filled with messages of sub-agents that finish their tasks, the main agent will pick the latest message. It will think about it, maybe update the user, okay, there was an extra progress that happened, and then it looped again, waiting for the next message. Again, this was our experiment. We figured there was another race condition in this situation. If you build something like that, there can be a situation where the main agent just fetched the message from the queue. It's processing this message and then fetches the next message from the queue. So it does resume twice without interrupting, which essentially will corrupt the state. To fix this, there is a lock, a simple Redis lock that will ensure that the execution doesn't continue unless interrupt happens. I also made here a little complexity bar so that you can follow with us. Like we started to feel like, okay, the thing is started to get a little bit bigger than we wanted to be. But this is all a part of experiment. So in a nutshell, this is the core of our architecture. Now we have concurrent arrivals. We have reliability so we don't lose the messages. We have a lock also helping with that. We can get our desired properties from here. So we can already update the user of the progress because we have the queue and we have main agent free to do that. But look carefully and you will spot that you cannot still get the user ability to course correct what's going on, at least in the architecture that we built. The reason for that is that the user, from this point of view of this system, you'll probably want the user messages go into the queue, which is what we wanted to do. So that it's simple. But if you have already 3 sub-agent messages in the queue, user's message will be 4th in line. So it's not interactive as you want it to be. The fix is also not so hard to do. There's a priority queue. This was the iteration that we went on. Okay, so now we have an even bigger system like that. So we built a solve machine and we thought about it and we see, all right, so now we have key desired properties we went ourselves to get. We have better accuracy, independent agents, working in parallel. The user can steer the incident mid-course. It can also be updated of the latest findings that were discovered. Imagine if this is an SRE agent, this would be the machine that you would want users to have, an agent that is truly interactive. But look also at the complexity bar, right? Like in the beginning, we just went to get more than one agent so that they do things in parallel. But now we also have the queue, we have a lock, and I keep pretending this works, but I'm sure you understand. So we have extra 3 pieces of infrastructure when we just wanted the agents to be interactive. And now this was an experiment. So then you're going to ship it. And when you ship it, you had one agent that is a service. Then you're going to have many agents. So you're going to have many services, right? That's the reflex that you want to have. And each of them has their store, checkpoints. And if something fails in the system, you're going to have to find a way to reconcile what needs to be fixed. And the delay and the last thing that we want from the SRE agent, the agent that is supposed to help you solve the incident, is for it to have its own problem and become even bigger of a pain for an incident. So we got to this point, and that's when we thought, so is this a cost of doing business? Is the distributed system tax that we have to pay if we want interactivity like that? It works, but it's also like a distributed monster now, right? We just want an LLM to do things faster. So then we started to, so this was an experiment. An experiment was essentially for us to learn what we can do, what works. And this is not in production yet. So there's also a benefit in that is that we can change things, right? So we started to think about, so if you have one agent, it's a service, it's a backend service, a process. If you want to have many agents, your reflex is to make many services. But then if you take a step back, and that's what we did, why do you want a microservice in the first place? You want things that probably are difficult, intensive on the compute, so you want to scale them independently. But this is not the case for the agent like ours and multi-agent system like ours, because an incident agent is essentially an agent that is intensive in I/O and API calls. You want to know why the node is down? Go check the metrics. It's an API call. You want to know the logs? An API call. You get all this data. Now you want LLM to reason about it? API code to LLM. The other reason is if you have many teams, but this was not the case for us. So we just decided to collapse it into one process, one service that has main agent, as sub-agents, as subgraphs of the line graph, and we have only one process in this. And just this simple simplification allows us to simplify the architecture a lot. We no longer need to think about how we're going to make them communicate over the network, how we're going to use Kafka, or is it Redis? Is it just the webhooks that will eventually fail to us at scale? No, it's all in memory and inter-process communication. The next thing that we also noticed is that the way we thought about it initially, I noticed the complexity just dropped, which is a good thing. If you have many agents, each of them, probably you want to checkpoint them, because if they break midway, you want to have a way to resume from the point they broke. That's why you have a database storing the checkpoints of what they did. So in our situation, an SRE agent is an agent that runs an investigation of sometimes very difficult problems in infrastructure. And sometimes it runs for hours, trying to figure out what's the root cause. It's very common for agent to run for hours to implement features when we talk to Cloud Code or something like that. So probably it's a good idea to checkpoint what it does, because if it fails in half an hour, you want to resume what it did. Is this also the case for the sub-agents? Okay, sub-agents also run for minutes, but not hours. So here's the trade-off, right? Either you keep precision up to second, or you drop the sub-agents. And our decision was to drop sub-agents there as the ones that keep the checkpointers. So we only have one checkpointer now, only one source of truth. The trade-off, of course, is if you have sub-agent that fails, you're going to have to restart it from the scratch. But that's just a couple of minutes that you lost at the cost of a lot of complexity that you reduce, and probably a lot of less things that will break in production in the worst moment, like in the incident. So back to the original system that we experimented, nothing changed. We still have a priority queue, still have checkpointer and lock, except the priority queue no longer needs to be a distributed Kafka, because everything runs inside of the same process. You can spawn sub-agents in the same process, and using dependency injection, you just tell them, this is the place where you have to write your updates. The agents themselves are ephemeral, they can die, we'll start them again, we'll lose a couple of minutes, but hopefully they don't die every minute, so this is okay. And the main agent is durable. So we have still all desired properties that we went for. We have interactivity because the user can course correct and user is updated. Things can be in parallel and fast, but at the half of complexity from the beginning. And this is the takeaway to take here, and as at the core of our PagerDuty experimentation. We build things ourselves first before putting them in production, and then we think about what it will cost to put them there, and is it the better way? And this allows us to simplify a lot. And we got to the end. So if you're gonna leave this presentation, I would like you to remember just a couple of things about multi-agents, about mainly why would you make them, what would you want them to be, and how is it supposed to be built. We started to build multi-agents because we had a context route, we had instruction overload, we had no interactivity whatsoever. It was slow and sequential. We figured out that we want parallel agents. We want them to be interactive and run in the background, each with clean context. And how are we going to build this? Are we going to build it as a distributed system, or maybe just one process with one durable supervisor and stateless sub-agents and a simple mailbox for communication inside the process? Thank you very much. This was a pleasure.